So in one of our previous lectures and one of our previous videos, we kind of finished at this point of defining the relationship between these three key quantities in kinematic motion. So the position, velocity, and acceleration. And what we were pointing out is that we can relate these quantities to each other in this kind of flowchart way. Position, the rate of change of position is the velocity, the rate of change of velocity is the acceleration, and we can integrate the acceleration to find velocity and integrate the velocity to find position, and so on. And one of the key implications of this, and you will have seen these equations at school, but you might not have seen where they came from, is arriving at a set of equations that we can actually use for modeling a large number of problems in kinematics. And the basic assumption for these equations is that we have constant acceleration. And what that means is that our acceleration does not depend on time. In other words, we have dA by dt equal to 0. That's another way of saying that A does not change as a function of time. And if we have that important restriction, then we can actually derive a set of equations for modeling problems which are which depend on this constant acceleration. And this is really important for a whole class of kinematic problems, particularly motion under gravity. So if you don't have any driving forces and the only force acting on your particle is the force of gravity, well, gravity is constant near to the Earth's surface, and therefore we have this constant acceleration. So let's see how this leads to the SUVAT equations with which you may already be familiar. So if we have that our acceleration is constant, well, we have that our acceleration is equal to the rate of change of velocity. And again, remember, these are vector quantities, A and V. Well, we can integrate both sides of this differential equation with respect to t. So we'll get the integral of A with respect to t is equal to the integral of dv by dt with respect to t. And what that means is we can integrate both sides. And here our dt's will cancel out. If you're a pure mathematician watching this, please ignore that process. This is slightly more nuanced, but for our purposes, this is what happens. And we end up with an integral with respect to v. We can also put in some limits on this. So our acceleration between our two different times, well, time changes between, say, time equals 0 and some final time, let's call it t prime for now, but we'll change back to t later on. And our v here varies between some initial velocity, let's call it v0, and some final velocity, let's call it v1. And because acceleration is constant with respect to time, that means we can actually just take this outside our integral sign here. Okay, so we actually end up with let me get my pen back, A integral dt between 0 and t prime is equal to integral dv between v0 and v1. And these now are trivial integrals, okay? We're basically integrating 1 with respect to time. We're integrating 1 with respect to v. And so what this implies when we integrate both sides is we're going to get A times the when we integrate 1 with respect to t, we just get t between t prime and 0. That is equal to v between the limits v1 and v0. And of course, then we can just substitute in our values here. And when we do that, we will get, so we'll get A times t prime is equal to v1 minus v0. Another way of writing that is v1 is equal to v0 plus at, and I'm going to leave off the, well, let's in fact put it on there, and then we can relabel these things. So if we say that our final velocity, let's say that our final velocity we will label v, and our initial velocity we label u, and we just relabel t as t prime as t. Then all of these together give us the equation that you should be familiar with, v equals u plus at. Okay, that's one of our SUVAT equations. And what that means is if I know the initial velocity and I know the constant acceleration, and again, these are vector quantities, my apologies for not underlining those, then we can compute the final velocity after undergoing acceleration for a certain amount of time. That's what that equation gives us. Okay, but we can go further than this because of course we know that v here, v is just equal to dx by dt. And we can go through the same process again. So if we rewrite what we have here, we have dx by dt is equal to u plus at. So let's write that out. Dx by dt is equal to u plus at. And again, we can integrate both sides with respect to time. So I'll get the integral dx by dt is equal to the integral u plus at with respect to t. And again, we can do this thing where this becomes an integral with respect to position. And we can put our limits in here as well. So our position changes between, say, 0 and some final position. Let's call it s. And here our time varies between, again, some initial time 0 and some final time t prime. When we do this integral then, well, integral dx will just give us x between s and 0. And integral u plus at with respect to t, well, bear in mind that these aren't constants anymore, okay? U is a constant, a is a constant, but at, of course, depends on time. So when I do this integral, I will get ut plus, well, if I integrate this with respect to time, I will get t squared divided by 2. So I'm going to get at squared all over 2. Fill in my little underlines there as well. And this is between 0 and t prime. Hopefully you can see where this is going. Now if I substitute in my limits here, I'll get s, which is this vector quantity called displacement. And on the right hand side, I'm going to get ut plus a half at squared. Which is, and again, I've kind of implicitly relabeled t prime to be t here, okay, just so this is in the familiar form. So this is our second SUVAT equation. So we have two equations that we've arrived at simply by using the fact that acceleration is constant with respect to time and the fact that we know the relationship between position, velocity, and acceleration. So we have v equals u plus at and s equals ut plus a half at squared. And if we now take equations 1 and 2, and I'm not going to do this in the video, I'll leave this as an exercise, but if you take equations 1 and 2 and find an expression for t, okay, you can do that, and then substitute that back into one of the equations, I think equation 2, then you will find that we end up with the following equation. Let's see, 2as equals v squared minus u squared. Okay, where again we have all of these vector quantities, our acceleration, our position, our final velocity, and our initial velocity. And you can find derivations of this in the Halliday and Resnick textbook. You can find them online in plenty of places as well. This is the third of our SUVAT equations. Okay. And with these three, basically you can compute the solution to many of the kinematic problems that we'll see, including things like parabolic motion for projectiles and so on. Okay, that's the end of the video.